Sodre, and he's going to talk about stochastic processes.
Well, thanks very much for having me here. Thanks for the invitation. I'll turn the lights so you can see better. So the goal of this talk, what I want to achieve is to give notions that pertain to the study of stochastic process, looking at a very simple one and a very beautiful one, which is the run and walk. So this talk is it's kind of informal in that sense, because we are looking for more for intuition than being rigorous or presenting tons of proofs. In particular, I'll be avoiding measurability issues that come when you do research in probability. That's suppose say I'm a grad student here, and my research area is probability. So that's why the title, Run a Walk, Stochastic Process, but bear in mind that the goal here is really going for the intuition and of concepts that are quite natural when you think on those objects. So the first thing with what is a stochastic process, you just think of a sequence of random variables or a family. So you can index countable if you have a sequence, or a family if you have a continue of random variables like an xt, and t belongs to R. And let's consider a very simple case when x is IID, which is independent and identically distributed, and they take values in 1 or -1, so it's a Bernoulli random variable. And the probability of success, so you say 1 is P, and probability of failure is 1 minus P, what we call Q. And we start with x0 equals 0. So that's kind of the general definition. I mean, roughly leaving the space, probability space in which those guys live behind. And this is a very simple example. Just tossing coins. Is that. And we can define a simple run and walk, the most simple run and walk, as the sum of this IID random variables. And it's another stochastic process. Okay? So, and that's the stochastic process we're going to be looking at. It's absurdly simple, but it's very rich, and it gives a lot of things to think about. So I like this object a lot. Okay. So first, since I defined this particular random walk as the sum, well, a random walk is a sum of IID sequences, but this particular one in which you go from either 1 or -1. What do we know about IID sequences of random variables? And we have first those two famous, that we see in probability. 101, that if the first moment or the expectation it's finite of xn, and since they all have the same distribution, all of them will be finite. I have the strong law of large numbers. So this should be x1, not x0, because I define x0 to be 0, but x1. And if the variance is finite, so this means that the empirical average converges to the expectation of the variable. And if I scale properly, I have the central limit theorem. I need to add that the variance is finite. And it means that the distribution of this empirical average, when I scale properly, converges to a normal distribution, 0, 1. So that's very simple facts about IID sequences of random variables. Okay, before I move forward, let's just take a look at some realizations of a random walk. So you you see each one of those colors is a path that has been taken. So you keep the balance of your, think of SN as your bank account, and then, or your account when you're gambling. Every time you see heads, you get $1. Every time you see tails, you lose $1. And you're allowed to be in debt. And another way to think about in terms of stochastic process is that you are picking a random path. So when you have, for example, a normal distribution, and then you go on your computer and then ask me, oh, okay, give me a number, draw a number for a normal distribution, get a number. When you see a process, you may think of picking a trajectory. And this trajectory is random. So very, very simple concepts. So now that everybody's comfortable with SN, what we're doing here, tossing coins and keeping track of what's going on. So no much mystery in that part. Let me come back to the slide. There's probably something wrong. Let me just check. Okay, that was a page. But what is? I made a mistake on the on the slides. But anyway, let me ask a first question. Let me define this n1 or n just as an inf of k, and k must be can be bigger or equal to 0, such that my random walk hits level 1. And n is a random variable, right? Because in this trajectory here, n equals 1, and this other trajectory here, n equals 1, 2, 3. N equals 3. So it really depends on the trajectory that you are looking at. And it is possible to actually find the distribution of this random variable. So it's possible to compute the probability that n is equal to n. And let me ask you, what is that probability when n is even? 0, right? Because I start at 0. So I can on 0, on 2, I'm always on even numbers. So I cannot hit 1. But so it's 0 here. And if it's not even, so in the case n is odd, so this is n even, n is odd, this is computable. I don't remember by heart the formula, but you can compute that using the techniques of, so it's bigger than 0. Okay? So, but, okay, so that's the first random variable that comes out that is derived from this random walk. And I will claim that this random variable is an example of a stopping time. So we see that this time is random. So it depends on the realization of the path, but it's random, and it is actually the first concept that pertains to a larger class of stochastic processes, and I can talk about. So what is a stopping time? And I think I have now coming back to... Yeah, I will turn off the light. Thank you very much. So a random time, just like, for example, n, is a stopping time if all I need to know if it happens is information that I have either now or in the past. So I cannot go into the future to figure out if my random time have happened or not. So this sounds a little bit strange, but we can give a little. So a stopping time cannot rely on information about the future. So we can think about these 4 candidates and think about what their stopping times are not. So the first time a run and walk reaches level K, is that a stopping time? Yes, because when it reaches level K, I am seeing that reach level K. So I have my clock. I started when the run and walk started, and 1, 2, 3, when reach level K, stop the clock. So then I have a stopping time. The last time the run and walks reach levels 1. So my walk reached levels 1, and then it run, it wander to infinity and never come back. Is that a stopping time? No, because I mean in order to make that call to stop my clock, I need to look at the whole trajectory. So stopping times don't allow me to do that, to identify things, to rely on information of the future. Some things that are stopping times that you might hear like a lot on investment, propaganda, or advertising, something like the time that suppose you have another stochastic process that gives you returns on your investment, and the guy promises to maximize the value of your balance in 1 year from now. He will stop it at your maximum amount of winnings or something like that. He cannot know that, right? You go to a casino and you will say, well, maybe the less you run a streak of luck and you reach, you gain $100, but you might play another time and win more, or you just might lose everything. So this is not a stopping time, and you see those are random times. But not all of them are stopping times. The stopping times play a very important role in probability theory. So another example, real life. The next time UT football team will beat OU, I think OU is the rival, something like Oklahoma. I don't know. I don't follow. By at least 10 points. I mean, that's a stopping time because I can't stop my clock. So. See, that idea of stopping time is the intuitive idea is that. So let's continue. Here on the end that I define. This stopping time is allowed to be infinity. Maybe the UT Austin team will never beat OU by 10 points or more, which I don't know. Perhaps people might be sad about this, but it might never happen. So in that case, I never stop my clock, and it's fine to have a stopping time that might take that as infinity. In this particular time that I define here as n, is the first time I hit level 1. There is a chance that if I don't have a balanced random walk, there is a chance that I never reach level 1. It's P over Q. You have to do those computations. They're quite demanding, but I mean they're not very difficult to do. And another question is that, okay, what's the expected time until I hit level 1? And I found out, well, it's infinity if P equals Q. And, okay, it's 1 if P is greater than Q. And the intuition is that when I have the probability of success being bigger than probability of failure, that my trajectories tend to go up, tend to reach higher levels and have the drift to go up. So I will reach level 1 for sure in a finite time. But if I have a tendency to lose on each toss coin, then my trajectory is pushing downwards, and I might not even reach level 1. And also you can compute the expectation of n, and you find out that In this case, when Q is, in the case that Q is bigger than P, I have the probability of being n being infinity is positive. Therefore, the expectation is positive. But on the other cases, I has also in that the balance case that the expectation of reaching the first level is infinity. It's already a kind of a striking result. You mean I will reach level 1 for sure at some time, but my waiting time has an average of infinity. And so that's the remark here. When I have a balanced random walk, the probability of hitting 1 at infinity is 0, but I still have the expectation is infinite. So it might take a long time for me to hit level 1. So let me ask a question. So let me come up with another stopping time. Let n2 be a random variable that counts how many steps it takes to go from level 1 to 2. What is the distribution of n2? Given, given, so to go from, so if my walk reaches 1, I start counting, start counting until we reach level 2. And what is the distribution of this random variable? Yeah, it's the same as n1. Here I departed from 0, toss my independent coins, I stop my clock when I reach 1. And what I'm proposing is once I am 1, I start throwing my coins, I stop when I am at level 2. So those two random variables should have the same distribution, since everything is IID. So you can construct then a lot of stopping times and numerous on this kind of walk. So let me discuss one that will play a role later in another concepts that I want to introduce, which is the first return to 0, which is the first time after, I start my walk at 0, that I will hit the 0 again. And after doing some computations with the probability generating function and some nice tricks that I am omitting here, one can show that is 1 if P equals Q, is 2Q if Q is less than P, and 2P if P is less than Q. And again, the expectation, although when P equals Q and then we have a balanced random walk, the expectation is infinity. But then I ask you the following question. So when P equals Q equals half, the return to the origin is guaranteed. However, the expected time for that to happen is infinity. So it might take, the intuition might take a long time. And so now, suppose that I am in the balance case. How many times the walk returns to 0? What? Infinite number of times. Infinite number of times. Because once it returns to 0, I can forget everything that happened. And then I start as if my walk started again. Then I'll hit 0 again in a finite time. And then I hit 0 again. So the number of times that I cross 0 is infinity when I look at the whole path of my random walk. So suppose the walk is at level 2. How many times the walk returns to level 2? In the balance case. In the balance case. Sorry? Suppose that I am, my random walk is at level 2. I'm seeing S equals 2. And P and Q equals half. I'm asking how many times I will go back to 2. Yes. Because, again, I just, instead of thinking of starting my run and walk at 0, I start my run and walk at 2. And then I will come back to where I started once more, and then I restart it over again, everything, and then we'll come back. So once I reach any level, I am sure I will come back to any level. Okay? And this is an example of Markov property. Markov property, and there are several processes that have this Markov property. That what happens in the next in the walk only depends on where the walk is now. So can you turn out the lights a little bit? So whatever happens here in the future, given that I am level 1, how do I get here? It really doesn't matter. Please.
So does that imply that eventually you hit every number? Or every element?
It will. If we combine the two, we're going to discuss that. But it does. This and the fact that the first stopping time that I discussed is also happens. You need the two things, but it will. That's a very good question. He asking, oh, does that imply that we'll hit every number in the balance case infinite often? And the answer is yes, and we can reach that conclusion, look at the two stopping times that I mentioned. But again, what is happening next, the next toss coin, and what happens with the S, it really depends on how I am at the present. It doesn't care how I reach that. And this is called the Markov property of any stochastic processes. And in this random walk, it's kind of quite simple to see. It's going on. So it really depends on how I am, how the walk is right now. So just got from Wikipedia, very lazily. But I mean, I read it, and it's kind of a process satisfies, so you can think of a general process that satisfies the Markov property if one can make predictions for the future of the process based solely on his present state. So I don't have to look at all the past again. And just as well as one could know in the process full history. It doesn't make any difference whatsoever. So conditional on the present state of the system, its future and past are independent. So nice. So we discovered now our second, that is the Markov property. And this applies to not only to the run and walk and the way I'm presenting it, but to other processes as well, and in particular to Markov chains. Please.
Could you possibly give an example of something that's not a Markov process?
Yes. Let me think. You can always think of your xn is equal to 1 if x0 equals to 1, and minus 1 if x0 equals to minus 1. So that's a stochastic process, and it surely depends on what first happened. This is a very simple example, because if I start here at 1, I will always get, and then I will consider the sum, right? I'll always go up, and if I start at minus 1, I always go down. But it's a legitimate stochastic process. It's a silly one, but it doesn't have the Markov property.
I mean, if you could rewrite that to make it have the Markov property, then is it just about how it's defined, or is there something about the process that tells you whether it's Markov or not?
It is. So you can think of the history in terms of if you are you can think of you have a those things are defined in the probability space, the whole process, Xn. And you can think of, well, F would be the sigma algebra containing what elements you can measure or not. And you can think of the filtration, which is basically all the information that which are sub-sigma algebras that have all the information that you have up to time n. And they contain the sets. I'm trying to avoid measurability issues. But what I'm saying is that the law, the probability of what happens in as future, given what has happened in the history f past, is just equal to the probability of as future what happens now. And you can, I guess what I'm trying to say is that you can make those definitions rigorous with the use of measure theory and sigma algebras, but I'm not going in that direction. But is that what you?
No, I was just thinking because the example that you gave, I don't know that really. I think that one is still Markov.
It's never positive.
Yeah.
Oh, okay. Maybe I should put. Oh, yeah. The example that I gave is still Markov. Okay, I was trying to be clever. Yeah, okay, because definitely still Markov because it's only a reproduction. Yeah, thank you very much.
But isn't
It's still Markov.
the future still dependent on that one in the past?
Yeah, it's a Markov. The example that I give to avoid Markov, it's Markov. So sorry about that. Well, let's try to get an example which is not Markov.
Say if
Help me.
X0 is
Yes.
1, then it goes down, and if X0 is -1, it goes up.
If x0 is okay, let's find a way. Let's find a no Markov process. You're suggesting.
If X0 is 1,
Okay.
then Xi is -1.
Xi is -1.
If X0 is -1, then Xi
You have I think you have the exact problem.
Yeah, exactly. Because
The exactly same issue.
Just
Okay.
just
Okay.
imagine a frog. This is Zikovich.
Yeah, sure. Let's find a no Markovian
So
process.
this is Gordon Zikovich's favorite counterexample.
Sure.
You imagine you have a frog jumping between, say, 4 lily pads.
Mm-hmm.
And so, the first step, it just has, say, chance, 1/3 to jump to any pad.
Uh-huh.
But it remembers the pad it came from. So next it would have 1/2 to jump to the remaining 2 pads.
Mm-hmm.
And so there, it would not be Markov. Because if you just know you're at a pad, then you have 1/3 to go to any of the other ones. But if you're at a pad and you know you were at, say, a previous pad, then you only have probability 1/2 to go to the 2 remaining ones.
Yeah.
So that one would be Markov.
Is that covers the counterexample? Thank you.
If you want a more physicsy example,
Yeah,
so
sure.
in physics, often the motion of something depends not only on its position but also its velocity. So you could imagine a random walk where your probability for the next step, your probability distribution for the next step, it depends not only on your current position but also whether you went up or whether you went down the last time.
Yeah. Okay. Good.
You could just say, no, I don't.
Okay. Please.
Could you have something like you're starting with, say, the first 10 integers and you're always doing a running average?
Running average, yeah. That's fine, yeah. Also no Markovian. Running average, yeah. Got varying examples. We're good. Okay, so the primary example of Markov processes are Markov chains. And what the idea behind Markov? What's kind of intuitive the why we go to Markov processes and they become very they are studied a lot. It's because if you think of modeling a phenomenon with IID things, just IID, like the position of a particle to be in IID at every time, you're not modeling that quite well. Right? Imagine that you have, and you say, well, the position of my particle is here, and then in the next moment you just pick IID again and it's here. Because the fact that your particle was in that corner tells you something about what the particle is more likely to be in the next period. On the other hand, if you try to model the behavior of this particle using the full history, things might get very complicated. So the Markov processes are kind of a compromise between those two things. You abandon the IID idea, but you still just say, well, the whole path doesn't matter, just what matters right now. So in that case of the particle, I mean, once the particle is there, I don't care how it came to be there, the whole path, but I will assign more probability to the particle to be in that area on the next period. But I don't care the whole path of this particle, you know. So it's a trade-off between, you know, accuracy. And so systems that are not Markovian, of course, tend to be more complicated to analyze in general. So, and Markov chains are examples of Markov process. And next thing that I will talk a little bit. So, okay, we cover Markov property, and hopefully we'll cover Markov chains. Of course, I'm not covering everything. I mean, it's just giving like good intuition of hopefully what those things are. So again, our run and walk can take values in Z. And we notice that it has the Markov property in the sense that if I pick integers in Z, the probability of being I given that I'm in J only depends, it doesn't depend on the whole history, like here. The probability that I am in IN given that that I will be in IN given that I am at IN minus 1, and the full history does not depend on what I was before. And I know how to compute this Pij's in the case of the random walk, which is P if E equals J plus 1, Q if E equals J minus 1 is 0 otherwise. See, my random walk doesn't jump from 0 to 2. It has to go through 1. So, and from that I can construct a matrix, and this matrix contains in this case is an infinite by infinite matrix, but a Z by Z matrix, but I don't mind. So that basically tells me, so if I put 0 here, and I put 0 here, minus 1, 1, 1 minus 1, that I'll have PQ. The rest, whatever you see lines, you're seeing 0, and you have P0, Q, P0Q, and the rest is. So this matrix tells me, if I look at the one entry, it tells me the probability of jumping from state I to state J. You know, given that I am on this state, what's the probability of jumping to that state? And we say that this is a stochastic matrix or a Markov matrix because the sum of each line is equal to 1. Okay? Because it has the probability, given that I'm that state, here I put the probabilities of going to another state, so better sum to 1. Otherwise, I'm in a very weird model. And also all the entries are positive, or no negative, to be more precise. So that's what the random walk has this matrix representing this jumping probabilities from one state to another. And you think of the random walk as having a state Z, the state space being Z. And a Markov chain is, if you consider S a countable or finite, if you want, countable, at least for this talk, and P a Markov matrix. As I said, the rows add up to 1, and each entry is no negative. You can construct a stochastic process from that. So all you need is a matrix and an initial distribution for your initial state, Z0. And, well, you construct that by assuming that Sn equals y, given that I was in J, the chance that is given by this matrix, and I have the Markov property. Okay? So in the case of the random walk, we see the matrix P, but in the case of Markov chain, I can start from one distribution of the initial state and come up with a matrix that will give me the evolution of the state, if I follow these rules to go from one state to another. And a very simple example, I have a two-state, S equals 1 to 2. I pick my matrix, 1 half, 1 half. So chance of being state 1, if I'm state 1, I still I stay in state 1, it's 1 half. I jump to state 1, it's 1 half. 3/4, 1/4 if I'm state 2. And then I just give a distribution for that. And what it is for this kind of Markov chain, the nice thing about it, there are many nice things about Markov chain, is that I can compute at a certain stage the probability that my system is a state I, just looking at these numbers, which are the entries of P to the n. And in a finite case, I know how to multiply my matrices. So it becomes kind of computationally easy to get those probabilities, unconditional probabilities. And as we've seen, the random walk is an example of Markov chain. Is that okay? Very good. So, but then when we study Markov chain, how many times do I have left?
20 minutes.
20 minutes? Okay. So when we study Markov chains, we start asking questions about the characteristics of that Markov chain. So we can always define by a transition matrix, Markov matrix, stochastic matrix, whatever you want, and an initial distribution. And we say that a state I is recurrent if the chain returns to I in a finite number of steps. And positive recurrent if it's recurrent and the expectation of timing of reaching the state I is it's finite. And new recurrent if it's recurrent and the expectation of reaching state I is infinite. And otherwise it's transient. So if all states are recurrent or transient, the Markov chain is then called recurrent transient. So the idea is that at some point I will reach any state, regardless of how I started my system. Okay? So recurrence and transience are characteristics of states and of chains. And then we can come back to our and ask when the walk, simple walk, is recurrent or not. Well, if I have the first return to 0, I know that is fine. I know that is almost surely finite only in the balance case. So I only have chance of recurrence. By definition of recurrence is that I'm gonna for sure achieved another all the states with for sure, and the state 0 in the case that I have an unbalance, I may not achieve it, I may not return to that with positive probability, therefore that chain is transient, and in this case it's recurrent only if I have the balance case, half and half. And again, recall that also for the balance case, the probability of hitting 1 when I start at 0 is then, again, a finite random variable. I mean, the number of steps that I need is a finite random variable. Okay, now my claim is that with all this information, I can say that the random walk is recurrent, even though I didn't speak about, and that's your question, it was your question at the beginning. So combining these two stopping times, I can say that Markov chain is recurrent. And remember that the definition of recurrence means that I have to achieve all states in a finite time. So what's going on? So I mean, I'm claiming that I'm done once I see this. I'm not going after level 10 or level 11 or level. Is that any idea, the intuition, why I'm claiming that I already have all the information to claim this recurrence?
If you start from 0, the odds of getting n steps away from 0 is 2 to the negative n. So since you go to 0 infinitely many times, you have many times 2.
Yeah, that's a way of seeing. I'm not sure about your probabilities, but that's the correct intuition. Think about this. I know that I will come back to 0 infinitely often, right? So there is an infinite amount of times I'll come back to 0. And I know in order to get back to 0, I can always avoid going to 1. But then I have to go to -1, always, like be below 0. But such an event, such a trajectory, has probability 0. Because there is a positive chance that I go to level 1. So if I apply this positive chance infinitely often, it's like tossing a different coin now and never seeing tails. So it never happened. Like infinitely many and never seeing tails. So this kind of walk here that hits 0 and never goes to level 1 has probability 0 of taking place, right? Because again, I mean, I'll make that experiment infinitely many times, and I know there's a positive chance of hitting level 1. So at some point, my path will hit 1. Once I hit 1, I know that it's going to hit 1 infinitely many times again. And by the same reasoning, I know that in between those times it's going to hit level 2. And once in level 2, it's going to visit level 2 infinitely many times. And I can ask in the balance case, what is the distribution, let's call n minus 1. The time that I go to, the steps that I take to go to -1. What is the distribution of this random variable in the balance case?
Same as n1?
The same as n1, because everything is symmetric here. So by the same argument, at some point I'm going to reach level -1. And then I'm going to reach level -1 infinitely often. And then I'll reach, that implies that I'm going to reach level -2 and -3. So my walk is going to be oscillating and going higher and lower and higher and lower, higher and lower. You're going to visit every state, not only once, but infinitely often. You see, that's a nice structure going on here. If you take this walk if you look at the trajectory of this walk. So I reach every state. So you can do, as you said, computing those probabilities, but you can also use an argument just like I am displaying now. Okay? So that's all I need to know about to conclude this recurrent is really knowing that it hits 0 infinitely often. It actually hits 0 for sure. Then I know that by Markov property is going to hit 0 again, and I have a positive probability of reaching level 1. Then I can do this kind of ladder argument. I think it's pretty cool. So we cover Markov chains, and especially the concept of recurrence transience. When you study Markov chains, those concepts appear. And so my goal is to give you an idea how they appear in the run walk. Now, one of the last topics is martingales, and for that I'll need a little bit of more of measure theory. So all these things, tossing coins, happen in a probability space. And I can imagine this stochastic process F is a sigma algebra that contains all the measurable events, all the things that I can take a probability of in this sequence. And I can think of the history of the process up to the time n. So all the possible information coming from the process up to the time n. In the case of the simple run walk, is all possible outcomes, all possible trajectories that I can see coming from time n. And that can be translated into a sigma algebra that is contained in the bigger sigma algebra that has all the events that that this stochastic process that are measurable with respect to this stochastic process, and so I have not all the possible information but I have all the possible information up to step n. So it's a little bit of a measure theory going on there, but we can Fn is a sigma algebra, so it's a set of sets of my set of subsets of my state space that has some nice properties, but I'm not going to that. Think of information. I like to always to think of sigma algebras in terms of information that they give us. So in this case that I define loosely the Fn, the sigma algebras, the information that I have, what type of events I can measure. For example, the max of the random walk. Can I measure that? Can I when the same measure, say, assign a probability to it? Well, the max from 0 to k to n, yes, I can. Can always look at the trajectory and compute what is the probability that the max in the past. So that's an information that I have once I see n realizations. How many times the walk hit level 0? We know it's infinitely many times, but in the balance case of it, we can. But that's not something that I can measure only looking at the first n coins, any choices. So how many times a walk hit level 0 in n steps is something that I can measure. And this the max minus mean, but here I'm putting n plus 1. So that really is not measurable with respect to that story here. I'm putting some measurability under the rug, but I want you guys to think of sigma algebras as events that I can measure, sigma algebra Fn as events that I can measure given the information that I have on the walk. So the problem in this case is with the n+1 here. So it requires information from the future, which this sigma algebra doesn't have. So, and of course, as the time passes, more information I gather, you know. So one sigma algebra is contained on the other. So a filtration, in that sense, that history is a sequence of sigma algebras that is increasing, because the more I see of the walk, the more information I can, more things I can tell about it. So in the case of p equals q, I can just make this question: what is the expected value of the random walk given the history up so far? And in this case, I can use taking the history x0, x1, xn, and I claim that it's xn. Is that clear? Why? Okay. Maybe I should do this. So expectation of Sn+1 given x0, x1, xn equals to expectation. By definition, this is xn+1 plus I equals 0 to n of xi given x0, x1, xn. Well, this I already know, right? Because it's given those random variables. So I can put out of the expectation, so I get expectation of n+1 given this whole x0, xn plus the sum equals 0 to n of xi. Those already happened, so I take out of the expectation. Well, this is Sn. This is independent of that, right, because of IID assumption. So this is equal to expectation of xn. And in the balanced case, this expectation is 0. So given the history, my best, in terms of mean, my best projection is the state that I am now. Even though I will never be on that state. Because if I am on level 2, I might go either to level 3 or level 1. But on average, I expect to be on level 2, on average, taking the average. So that's very loosely speaking. So it has this R random walk, if P equals Q, has this property. And if you think of a general stochastic process and a filtration, this is an increasing sequence of sigma algebras that have the information, I can say that Zn is a martingale with respect to the history if it's, the expectation is finite. Sn is Fn measurable, so it means that the information that my sigma algebra contains and the information of this random variable provides, they're in some sense compatible. And the expectation of Zn plus 1 given history equals Zn. So this is a martingale, general. For any stochastic processes, we have at least, I'm given the definition for a countable case. And we discover one more property of one more definition that we can make sense looking at the simple random walk. But it might happen that if happens that z plus 1 given the history up to time n is bigger than Zn, then I call this a submartingale. And if inequality is reversed, I call it super martingale. And the theory of martingales is very beautiful. In particular, we have convergence results for martingales. Normally, when you look at a process, you might wonder if it converges in some sense, in law or in almost sure sense to some random variable. and having a martingale gives you, other certain conditions give you convergence results that I'm not going into this talk. And as a small exercise, I mean, if a random walk S is a martingale with respect to story, if P equals Q, and what if P is greater than Q, then what we have? It's a super, I claim that it's a sub-martingale.
So if you take the group of or the set of all like sub-martingales or martingales and martingales, is that more specific than just saying it's a Markov process?
More, yeah. I mean, I can have. I don't know. I mean, there are different definitions, so I don't need to have a Markov process to have a martingale. I mean, yeah.
So
I can cook up an example in which I don't have a Markov process, but still have a martingale.
Okay, but if it is a Markov process, then it must be a martingale.
No, the example is here. If the random walk is not balanced.
Or if it's a Markov process, does it have to be one of the three like sub-martingale, martingales, or martingale?
Well, you always can give counterexamples playing a little bit with this filtration, you know. So that's, I think it's an easy way out of your question being no, because I can always play with I can put other random variables that make this filtration come up with the information. So my answer would be, my first guess would be no. I can go, in principle, different concepts. Yeah, one does not imply the other way around. Okay. But that's a very, 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 very good question. So there is given this sets of slides online, and there's a this is from Gordon Zikovich notes. It's a nice example of a martingale that you can compute. Like union urn contains B black and W white balls on, and the game is the following. I pick one ball at random, and then if I pick black, I will replace with 2 black balls. If I pick white, I will replace with 2 white balls, and I keep doing that. That forms a process. The proportion of black balls at time n forms a stochastic process, and you can prove it's a martingale with respect to the natural filtration of what you, the natural history of what you've done so far in that exercise. So yeah, you can prove that, and there's some hints, and I can let this available to it. And so the last topic, I still have.
If you want to say like a few more minutes.
Yeah. Last thing is that one of the most studied stochastic processes, and now it's continuous time stochastic processes, is the Brownian motion. Let me just give quickly the definition of the Brownian motion. So we have a stochastic process now in continuous time, Bt. So it's indexed by t belongs to r. That's why we call continuous time. Not that t means time or anything like that. So if 1, b0 equals 0, 2, I have independent increments that basically means that the value of t given, it's the value of b t minus bs, and of course t bigger than s, given b s minus bq, So those are two increments that I take from here to here, and I look at the difference, and I look at the difference from where I pick it up, the increments, and they are independent, and then Q for T bigger than S, bigger than Q. And what is the other property is that BT3 minus BS, it's a normal distribution, it's not only a distribution with variance T minus S. And you see the Brownian motion looks like that if you simulate it. And it carries many properties of the simple run and walk. Actually, one way to prove the existence of such subject is to think of a simple run and walk, a balanced one as we presented, and today, and think of dividing this grid here and making the time steps smaller and smaller, as at the same time making the jump smaller and smaller. If instead of jumping to 1 and minus 1, I jump at time increments, I jump less and less, but I still, with equal probability, somehow take the limit in a reasonable sense, and I have the Brownian motion. And many of the characteristics of transience that we discussed, if you look at the path of a random, of a simple random walk, and you connect, so this is our the realizations, but if you connect that, you get a continuous function that is not differentiable here on the kinks, on the jumps, right? But here, when I take this limit, the jumps happen all the time. So the Brownian motion is, the path of a Brownian motion is continuous, but is no differentiable everywhere with probability 1. Transience goes, and it's no wonder that I have normal distributions here. One of the ways to actually prove the existence of Brownian motion with much more care is doing this process of dividing, chopping up this, and making this time steps a little bit smaller and smaller, and making the jump smaller and smaller in the right scaling. And I have something that was Bernoulli, and now I have something that is normal. So is any intuition why I'm getting this?
Bernoulli distributions and normal distributions look the same, look like large sizes.
Any distribution, you know, central limit theorem, IID. Yeah, for the IID, I'm getting normal. So if I want to, a process like that has these properties, but if it doesn't have the normal property like that, that object does not exist. And what is plain a row here is really central limit theorem. So that's why I got normal things. And again, since I started with the balance things, go up and down, crosses zero infinitely often, and has many properties that carry over from the simple run and walk. So that's it. I hope you enjoyed, and if you have any questions, please let me know.
I never got why we specifically chose T minus S as our standard deviation.
What?
For the last part of Brownian motion, like increments are normal with T minus S as standard deviation. I don't know. It's a very random question. I just never got why we picked that.
I think one of the, if you go into that Resnick, there is this nice book. I'll just give you Adventures in Stochastic Process that goes on the part of the Brownian motion. They do they don't prove the Brownian motion in that way, which is possible, that way of slicing, but they give a nice intuition, and it might clarify for the details. Yeah. So I think it's chapter 8 of that. That gives, that uses that intuition. They prove in another. I saw at least 3 proofs of the existence of Brownian motion. So the one that I saw doesn't get that. And by the way, I'm very interested. I mentioned this book, Adventures Stochastic Processes. it's a book that is, you can, in order to do, it's a final word, in order to do research in probability, you need to really go into measure theory, especially there's some parts that are a lot of things that put that under the rug for the sake of intuition. But research requires mastering of such measurability issues. But this book is very nice because you can start learning things basically with adventure in stochastic process. And if some of you wish to read this book and would like a guidance and solve some exercises, I'm actually, I found this book very interesting. And the good thing is that you can open up and start working on right with low level of measurability. And the first chapter is, you'll find this discussion of random walks. The second chapter is a discussion of Markov Chains. Has plenty of good exercises, so there's any interesting of reading that book with me and discussing any part. I am always looking forward to solving some challenging exercises. Also, the exercises on this book are amazing in terms of intuition. Any other questions?
Looks like our speaker.
Yeah.